Hey guys, welcome to our video lesson plan about supercritical fluids and supercritical fluid extractions. This video lecture series will cover a wide variety of topics, including the basics of supercritical fluids, applications of supercritical fluid extractions in industry and lab scale operations, as well as touching on the basics of safety and process design for these kinds of extractions. In this video, we're not going to cover all that. We'll just cover only the basics of supercritical fluids, what an extraction process looks like, how unique and broad supercritical fluids extractions are in chemical engineering. So let's get started. Okay, what is a supercritical fluid? A supercritical fluid is a substance that is subjected to a temperature and a pressure above its critical point. So these fluids exhibit properties intermediate of both liquids and gases. I provided here a few graphical reminders of what supercritical fluids look like, which could be helpful. If we look over here on this first phase diagram, you can see up here this red region represents the supercritical fluid region, where the critical point is right here. And if we look over here, I have this other phase diagram. It kind of just displays this kind of, this gradient of where certain regions of the supercritical fluid region represent more gaseous, properties. This region up here would be more resemblance of liquids. I've also provided this pressure versus enthalpy graph for another graphical reminder of where or of how supercritical fluids. The supercritical region is shown up here in green, where this critical point is this point in red, right above the two-phase region, the vapor region, and next to the liquid region. Okay, moving on to the transport properties and solubility advantages of supercritical fluids. Important point is the diffusivities of supercritical fluids are much higher than regular fluids. More resemblance to gases, actually. You can see that in this graph over here I've shown, or this table over here, the diffusivity constants of gases, supercritical fluids, liquids, comparing them, also the densities and the viscosities. This increase in diffusivity is a huge advantage over the liquids, as it improves solubility properties of the fluid by a substantial degree. Solubility is usually an important property to consider in chemical engineers, especially in the case, if we're talking about mass transport effectiveness. In order to achieve the selectivity and yield structures that we typically want from a separation or need for a process, we want to be able to fine-tune the solubility of the working fluid that's in the process. So, being able to have this advantage, or this diffusivity increase is a huge advantage. The diagram down here, kind of shows this molecular solubility difference, as a gradient from solid to gas. Really take note into how this, the supercritical fluid is between liquid and gas, and adjustable density and solvent power. Another important point to note is when close to the critical point, small changes in pressure and temperature can result in large density changes, which is important because it allows us to fine-tune these solubility and mass transport properties more exacting or more precisely. So shown here, I have the carbon dioxide density pressure phase diagram. This is also just repeating this point, showing that whenever we're close to this critical point right here, the density is changing very rapidly, especially on this 310 isotherm. It's important to note that the density is not the only thing that changes dramatically close to the critical point. Also, the viscosity, the relative permeability, and the solvent strength also change to a notable degree. Okay. Another important advantage to consider is the low surface tension that is found within supercritical fluids. Almost no surface tension, as there is no liquid-gas phase boundary that exists. This is helpful in making the fine-tuning of the solubility easier, and allows for better pore penetration whenever we have any kind of solid matrix or mass transport matrix that we need to work with. Some naturally occurring supercritical fluids, which I thought were kind of cool. They exist in hydrothermal vents, or in the seawater around hydrothermal vents, and within the inner atmospheres of some of the planets in our solar systems, most notably Venus, Jupiter, and Saturn. Temperatures and pressures of these regions are just right for supercritical fluids to form, and they exist in that region. Now let's consider what is an extraction and how is this connected. A liquid-liquid extraction involves the mass transfer of a target molecule between a solute and a solvent. The effectiveness of this process depends highly on solubility limits and the properties of the working fluids involved. Generally, it's best to maximize solubility of the solvent if one wants to achieve, a maximum mass transport between the fluids. Regular fluids usually don't always cut it. They have undesirable solubility properties needed, or they can't really achieve a high yield of mass transfer due to the constrictive diffusivity limits. That's where the supercritical fluids are advantageous. If a supercritical fluid is used as the extracting solvent, a supercritical fluid extraction can be performed, which, as discussed previously, these supercritical fluids they have much higher yields and selectivities due to the distinct property differences from regular fluids or regular liquids. Okay, just going to briefly mention the basics of supercritical fluid extractions and their advantages over regular extractions. The most common solvent used in practice in industry is supercritical CO2. Why CO2? Well, a few reasons. It has low critical pressure and temperature. It is relatively non-toxic. It is non-flammable, and it's easily available to experimenters in pure form, such as in dry ice and pressurized CO2 tanks. The overall advantages of SFEs are the selectivity and speed improvements over regular extractions, which is due again to the differences in diffusivity properties. Typical co-solvents used in industry are ethanol, methanol, and water, which are used to enhance the solubility power of CO2, making it possible to extract much more polar molecules from a solvent or from, a molecule of interest. The diagram here shows a typical process of an SFE. As it can be seen, the supercritical fluid is mixed along with the co-solvents or pumped in to the extractor tank. And then after it is sent to a separator where further purification is performed. Sometimes a heat exchanger is, included along here or before the extractor, just to ensure that the supercritical conditions are met within the fluid before the extraction occurs. As we'll see in the next few videos, this is not the only way to set up an SFE, but merely acts as a guideline for more advanced separations in more processes that are found in industry and in the cool applications that we'll see. Thanks.